Howdy, this is Chris Chen, and I'll be presenting the rest of the slides. So first of all, let's look at model complexity. We can see that state space models are good at speed and memory, big of L, which is linear, while transformers are quadratic. However, the performance of state space models are not as good as transformers. That's why the authors introduced Mamba. So the key contribution of Mamba, first of all, let's look at input dependency. So input dependency lets the model choose to remember or forget each input. So it can ignore noise or irrelevant data, and theoretically, it can improve the performance on longer context. So let's look at the copy and selective copying. So for copying, for example, we're interested in the blue, orange, red, and green boxes, and we want to copy them. So selective copying is that we want to kind of extract these four boxes that we're interested with a bunch of let's say garbage we're not interested in. And how well the model is doing this is selective copying. And for the induction heads task, it is trying to let the model learn the pattern that whenever we look at a black box, we'll have to infer the blue box. So how well is Mamba doing? Mamba is doing pretty good on input dependency. Its accuracy is almost 100% comparing to other state-based models. And for the induction heads, we can see that the longer the test sequence length is, Mamba is doing it is maintaining its accuracy about 100%. And while other models, including transformer-based ones, they drop pretty quickly when the test sequence length is getting larger and larger. Also, Mamba is good at fast training. We've already known that is big of L for time and memory for full sequence training. But I want to mention that text generation is big of 1 for a single token. And these two graphs clearly shows that Mamba is basically the best among all other models. So the speed is important. This Mamba model is performant compared to similar model sizes. You can see it's faster speed. Another way to say that is more throughput. For the bottom left graph, we can see that it is trying to compare scan and convolution and attention. These are ways to aggregate information. They want to show that scan is the best among them. And the bottom right graph, we can see that Mamba's throughput is the best among the four models. We can see that for Transformers 6.7 billion, which is a pretty large model, it basically gave up on batch size 32 due to out of memory error. So for general modeling, Mamba works on both discrete and continuous data. It does slightly worse for continuous data because of discretization bias. So what is discretization bias? To recall that, you can think of this as for you want to, let's say you want to reconstruct a continuous data, which is like a signal. For a signal, if we want to discretize it, we have to put let's say delta, like a time interval, to record that. And for Mamba, the delta is not fixed. It is based on the data. So it is more difficult for Mamba to reconstruct the information of the original signal. That's why you can think of why Mamba is not doing as good on continuous data than non-continuous data. So for the conclusion, the strength of Mamba, like we mentioned, it's long. It can have long context windows, fast compute, selective memory, comes with GPU optimization. But the weakness is biased towards continuous data, and it is essentially a compressive algorithm. And also, it is currently difficult to use due to technical implementations. That's why the results from study is actually limited. Here are other ongoing works related to Mamba. For example, Jamba is trying to combine Transformer and Mamba, and there are other papers. So that's the end of my section. Please feel free to ask questions. Thank you.